Hello, welcome to my talk on dimensional analysis, Buckingham pi theorem, the principle using an example. In this talk, I will first introduce the difficulties in the direct fluid dynamics, and then a brief introduction of Buckingham pi theorem and its advantages. Then we move to the detailed steps for using Buckingham pi theorem, the problem analysis, to identify the parameters involved in the dynamic system, and then the determination of base units and of the constructing parameters. I will tell you how and why in details. And then the construction of non-dimensional parameters. In this talk, an example is the flow in a horizontal pipe. This is a smooth pipe with a diameter d and the flow velocity v. The fluid density and viscosity are assumed at rho and mu. The target is to study how the fluid friction will change in terms of these environment parameters v, d, rho, mu, etc. As I have shown in my talk, the difficulties in dimensional analysis. For such a simple flow problem, the fluid friction is a function of four parameters: the fluid velocity, fluid viscosity, fluid density, and the size of the diameter of the pipe. To look at the dependencies of the fluid friction on these parameters, we need to change at least 3 times for each parameter. So the total combination would be equal or larger than 3 times 3 times 3 times 3. So it is 81. If we use the numerical way to solve the problem, we need to solve Navier-Stokes equation for more than 81 times. Or if we use the experimental studies to look at the problem, we need to conduct more than 81 tests. This including changing the models and the fluids. So we can see the difficulties in the data collection. And for the direct fluid dynamics, we may also have the problem of data representation to see how we can build the relation between the friction and the relevant parameters. And this is the requirement for the optimization of the design. So when we have all the data and we put all the data together in the plot, it would be the fluid friction, which would depend on the velocity, the diameter of the pipe, and the viscosity of the fluid. And this is only for one density of the fluid. However, we need to change the density of the fluid, so we have another plot at this, and for the third fluid density we have the plot at this. So again, we can see for the data representation in the direct fluid dynamics, this would be very difficult to see how the fluid friction dependent on these parameters. Now we have a good tool for simplifying such problem. The powerful tool is dimensional analysis based on Buckingham pi theorem. Principally, for the dimensional analysis, we have several steps. The first step would be determination of the total physical quantities or variables, for instance x1, x2, to xn in the dynamics, which could form a function either in a form x equaling to function f1 of the parameters x2, x3, and xn, or in a form of f11, the function of the parameters x1, x2 to xn, which is 0. The step 2 would be determination of the base unit involved in the physical variables, and then choose the original or constructing variables for representing this base unit. After that, we can determine the number of the non-dimensional parameters p equaling to n minus m. That means we have p non-dimensional parameters pi 1, pi 2, and 2 pi p. Then the dynamic function can be expressed as pi 1 equaling to function f2 of pi 2, pi 3, and pi p, or in a form as function f22 of the non-dimensional parameters pi 1, pi 2 to pi p equaling to 0. And we also see the detailed method for constructing the relevant non-dimensional parameters from the chosen variables, even if the detailed form of the function is unknown. Here we see how the dimensional analysis can simplify the problem. This is the first concept for your reference. In the direct method, the flow deflection can be expressed as the function f1 of the parameters v, d, mu, and rho, or in a form of f11 of the parameters the fluid friction, velocity, the diameter of the pipe, fluid viscosity, density is 0. So in the dimensional analysis, from this function we can see the total variables is 5 and equaling to 5. The variables we see here: fluid friction Fr, fluid velocity V, the diameter of the pipe D, the fluid viscosity mu, and the fluid density rho. And from the analysis of all these physical parameters, we can see the base unit would be 3, hence m equaling to 3, the base unit for mass, length, and time. I will show you why the base units are this later in this talk. The number of the non-dimensional parameters would be p equaling to m minus n equaling to 2. Therefore, we have 2 non-dimensional parameters in this dynamic system. After dimensional analysis, the function of this would be reduced to a function as this. Non-dimensional parameters pi 1 is the function of the non-dimensional parameter pi 2. Or similarly, we have the function f22 of the non-dimensional parameter pi 1 and pi 2 is 0. So we can see from the function, after the dimensional analysis, we can reduce the function of multiple parameters into a function of a single non-dimensional parameter. We can see dimensional analysis could simplify the fluid dynamic problem, and we will see more details in the dimensional analysis later on. Before the talking of the details of dimensional analysis, we need to see the concept of the base unit and the derived unit of the physical parameters. Here, we will talk about the base unit. This is given by the International System of Units in 1960. For all physical parameters, there are total 7 base units, and among them, 4 of the 7 base units may be used in fluid dynamics. The first 3 base units are mass, symbol capital M, its unit is kg, and length, the symbol capital L, the unit meter, and the time, the symbol, the capital T, unit, second. These three base units are the first base unit recommended by BAAS, British Association for the Advancement of Science, in 1863, and later on, with the advancement of science, more base units were added. For instance, temperature, the symbol theta, the unit is Kelvin, K. This temperature would be used if the heat transfer is involved in the fluid dynamics. And for your reference, there are other three base units used in different topics. For instance, the electric current, the symbol capital I, unit ampere, and the luminous intensity, the symbol is capital C, unit candela, CD. And the last base unit is the amount of substance. The symbol is capital N. The unit is mole, M-O-L. Now we have a look at the common physical quantities in fluid dynamics. As we mentioned in the previous slide, we have the base unit used in fluid dynamics: mass, unit kg; length, unit meter; time, unit second; temperature, unit K. And we have many derived units based on this base unit. For instance, velocity, meter per second. So the symbol would be given L/t power of -1. The acceleration, the meters per second square. So the symbol would be L/t power of -2, and etc. And we have also some very special derived units. For instance, angle actually has no unit, although we use radius, but it is not a formal unit. So the angular velocity has a unit per second. So the symbol would be t power of -1. The angular acceleration per second squared. So the symbol is t power of -2. And the frequency per second. So the symbol would be t power of -1, and so on. Now we are going to look at the detailed steps in the dimensional analysis based on the Buckingham pi theorem. From the physics and from our experience, the fluid friction in a horizontal pipe can be decided by the following parameters if the pipes are smooth. Flow velocity, as we can understand, a larger fluid velocity might cause a larger fluid friction. Pipe diameter. For a large pipe, the fluid friction would be larger. Fluid viscosity. It is understandable a larger fluid viscosity might cause a larger fluid friction. Fluid density might be also very important for the fluid friction, and we will see how important it would be based on the analysis. Hence, the fluid friction can be expressed as a function of the environment parameters: the velocity, the diameter of the pipe, the fluid viscosity, and the density. Or we can express the function as this form. So from this expression, we can see in this dynamic system, the total physical parameters N would be 5. Fluid friction, fluid velocity, diameter of the pipe, fluid viscosity, and fluid density. In the step 2, we are going to analyze the physical parameters in terms of the base unit, and based on this, we can determine the number of the base unit in the dynamic system. So in this table, we put the 5 physical parameters here fluid fraction, velocity, diameter of the pipe, fluid viscosity, fluid density, and their unit are given as this here. One thing here should be noted. For the force, we have the unit Newton, but in fact Newton is a derived unit. The former unit for force would be given as kg, meters per second squared. So based on the unit, we can see the base unit here, the mass, capital M, the length, capital L, the time, capital T, and the temperature, capital theta. So from this unit, we can see M should be 1 because kg here, and L 1 because meter here, and capital T minus 2 because this is per second squared, and theta 0 here. There's no unit for temperature. And similarly for the velocity, we have this and the diameter of the pipe, the fluid viscosity, and the fluid density. Also, we can see the corresponding symbol for these physical parameters would be given as mL T power of minus 2, L T power of minus 1, L, and so on. So we can see from this table, in this problem, we don't use the unit temperature. And from these symbols, we can see we have 3 base units, mass, length, and time in the dynamic system. So M is equaling to 3. That means in this dynamic system, we can use the 3 base units, mass, length, and time, to construct all the units of the parameters. In the step 3, we need to choose the original or constructing parameters to represent the base unit, mass, length, and time. Since there are 3 base units in the dynamic system, we can choose 3 original or the constructing variables from the identified physical parameters, no more, no less. And the constructing variables must include all the dimensions of the identified base unit, mass, length, and time. And again, no more and no less. That means the constructing variables contain only 3 dimensions, mass, length, and time. In fluid dynamics, for most cases, we can choose the constructing variables. For the base unit length L, we can choose D, the diameter of the pipe, or in many fluid dynamic problems, the general length of the structure in fluid. This is generally the first constructing parameter we have to choose because it has the base unit of length. And for the base unit mass, we can choose fluid density, unit kg per meter cubic. Why we choose this? That's because we can constructing rho d cubic. Here, d is already chosen. It would give the unit of mass. So that's why we can choose the density to represent the base unit of mass. And for the base unit time, we can choose the fluid velocity, unit meter per second. We can use d over v to construct a unit of time. Again, d is already chosen here. Generally, for most fluid dynamic problems, these 3 parameters, the length of the structure, the density of the fluid, such as the air density or the water density, and the fluid velocity can be chosen as the constructing parameters. only in the cases of heat transform, where the fluid temperature is needed to be taken as a constructing parameter. Step 4 is easy for determining the numbers of the non-dimensional parameters or groups. Since we already know the number of the total physical variables, in this example, n equaling to 5 for 5 physical parameters, Fr, V, D, mu, and rho. And also, we have identified the number of base unit, mass, length, and time, so m equaling to 3. Therefore, we should have the number of the non-dimensional parameter pi I. It would be p equaling to n minus m equaling to 2. That means, in this dynamic system, there would be 2 non-dimensional parameters, pi 1 and pi 2. This also means the function between pi 1 and pi 2 can be used to represent the dynamics of the system. In the step 5, we construct 2 non-dimensional parameters, which would be given as this pi 1 and pi 2. Pi 1 is based on the fluid fraction and use the constructing variables d, v, and rho. So we can construct the non-dimensional parameter pi 1 as this. And similarly for the pi 2, it is based on the fluid viscosity. And in the same way, use the constructing parameters d, v, f. The indices a, b, c, d, e, f are so chosen so to make pi 1, pi 2 the non-dimensional parameters. In the next few slides, I will show how we can decide the indices a, b, c, d, e, f. Here in this slide, pi 1 would be construct. Pi 1 is defined as this, and we also list the dimensions of all the physical parameters Fr, D, V, mu, and rho. Now we can substitute the symbols for each parameter in the definition of pi 1. So we have the expression as this. Here, Fr uses mLT power minus 2, and the D is L with the power of A, and the velocity and the fluid density. And we put all this together for each base unit m with the power of 1 plus c, and L with the power of 1 plus a plus b minus 3c, and t power of minus 2 minus b. Our target is make all these indices be 0, so the parameter pi 1 would be non-dimensional. So we can obtain the equation based on m. So we have 1 plus c equaling to 0. Therefore, c is minus 1. And on t, we have the equation minus 2 minus b equaling to 0. So b would be minus 2. And on L, we have the equation as this, and we can solve a equaling to minus 2 by employing the indices c and b into this equation. Then we can write the non-dimensional parameter pi 1 as this by substitute all the indices into the expression. And this is actually very similar to the conventional friction coefficient, Cf, defined by the friction divided by this expression. we see 1 over 2 here, but 1 over 2 is a constant, so the expression should be still non-dimensional. And the d squared is replaced by a general reference area S for general applications, because S has the same unit as d squared. So the non-dimensional parameter pi1 is equivalent to the friction coefficient CF. Similarly, for the non-dimensional parameter pi2, we can substitute all the symbols into the expression. So we have the expression for pi2, and we can write the expression as this based on m, l, and t. Again, since pi2 is a non-dimensional parameter, therefore the indices of m, l, and t are all 0. Thus, it would make the equation 1 plus f equaling to 0 on m. So we have f equaling to minus 1. And on t, we have minus 1 minus e equaling to 0. So e would be minus 1. And on L, we have the expression as this. So we can obtain d equaling to minus 1. Therefore, the non-dimensional parameter pi2 would be given as this. And we can see its inverse form is still non-dimensional parameter. And this is the famous Reynolds number, as we can see in the fluid dynamics. So basically, for the non-dimensional parameter pi2, it is equivalent to the non-dimensional parameter, the Reynolds number, Re. Now in the final slide, we will see a summary for the dimensional analysis. The original problem is looking at the fluid friction Fr as the function of the physical parameters, the fluid velocity V, the diameter of the pipe, the fluid viscosity, and the density. So this is a dynamic problem of 5 physical parameters. And using some magic operation, the output of the matrix box is a dynamic problem of 2 non-dimensional parameters, Cf and Re. Cf is the friction coefficient, and Re is the Reynolds number. So the problem is reduced to a simpler problem. Here we can see the friction coefficient is only dependent on the Reynolds number. And inside the magic box is the dimensional analysis, a powerful tool for fluid dynamics.